This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions about software engineering topics at least once a month. Thanks to our audience and the partners listed on our website for supporting the podcast. Welcome, listeners, to a new episode of Software Engineering Radio. In this episode, we're once again going to talk about something that relates to Scala. We had 2 episodes on Scala already, an introduction a long time ago, and the kind of update with Martin Odersky, I guess, maybe 5, 6, or 7 episodes ago. This episode is going to be on a very interesting Scala project, a middleware project called Akka. You probably heard about it. And on the other end of the Skype connection is Jonas Boner, the chief developer, I guess, and inventor of Akka, right?
Yeah. It's actually more than just me nowadays. I mean, when I was starting off a couple of years ago, it was only me. But now, the last year or year and a half, it's been a team effort. Some great individuals. So.
Right. So I guess Victor Klang, I think, is one I always read about on Twitter.
Yeah, he's one of the key core developers. An amazing guy, and we have others great developers as well. So I'm just one in the herd, basically.
Well, you're certainly the face that most people associate with Akka. So, do you want to introduce yourself a little bit so people know who we're talking to?
Sure. My name is Jonas Boner, and I live in Sweden, a small town called Uppsala outside Stockholm. I've been involved with Scala for about 5 years now. I got before Scala, I started getting into functional programming in general when I started off using Erlang. Long story short, I got really excited about Erlang. I tried to get people excited about it, clients and colleagues and so on, but it was really hard to push through because it's an excellent language, but it has its own runtime, it has its own libraries and so on. But I just basically felt it was too many good things to just be left to these Erlang geeks, and I wanted to move over or some of these concepts onto the JVM. So I started Akka about 2.5 years ago. Something like that. Before that, I worked at a JVM clustering company called Terracotta.
Ah, right. Yeah.
And in the meantime, between Terracotta and Akka, I was running my own consultancy firm as well. And prior to Terracotta, which I worked for about 4 or 5 years, I worked for BA Systems at the JRocket team, the JVM team. They have a team here in Stockholm, in Sweden. So I've been mainly involved in writing middleware products and systems, and also consulting in the area of concurrency, scalability,
right?
The server side and end of the stack, you can say.
Yeah. So when I looked at when I looked at Akka, it's clearly obvious that Erlang is an inspiration, right? So do you want to give us an overview of what Akka is and maybe what the main influences from Erlang are? I mean, we will talk about the various modules and stuff later, but just like kind of 10,000 foot overview.
Yeah, sure. It is definitely influenced by Erlang and but also by some other languages and tools out there. So I've tried to sort of put together a bunch of tools and ways of thinking that to a regular Java developer might sound a little bit alien, but that solves the concurrency and the scalability and the fault tolerance story in a very neat way. So from Erlang, we adopted the actor model of concurrency, which is an even better model over distributed computing. We also adopted the Erlang style of fault tolerance, of reliability, and also sometimes known as a let it crash, embrace failure. We can talk more about that in detail later. So we use actors for that as well. So we use actors for both scaling up on multi-core architectures, meaning embracing concurrency. We also use actors for scaling out on multiple JVMs. And you can do that using the same abstraction, the same runtime. So you basically you write your code once, not thinking about either of these. If you work inside the sort of the actor model, you obviously sort of prepare your application to scale either up or out, and sometimes both. And since you have this level of indirection, the runtime can actually even take that decision for you if it should be scaled up or out.
So in some sense, you're saying that developers once have to learn something that may feel a bit strange in the beginning, but then they're kind of settled and can do everything they need.
Yeah, more or less. I just want to respond to that actors are sometimes, in many cases, an excellent tool for the job, but there are certain kind of problems that actors can't solve at all, where the actor model sort of falls apart, and that is, for example, when you need consensus across many concurrent components or even distributed components. Actors implements the contrary of that. They implement shared state. Share nothing architecture.
Share nothing, pure message passing, basically.
And the classic way you solve that in Erlang and in other tools that or frameworks that implement that is by shoveling everything down into database. In Erlang, you have the Amnesia database, or if you're in the Java space, you would probably put it in MySQL or something.
Right.
And only in doing that, only when you need something like consensus is extremely expensive. Why should you pay for the I/O overhead and the disk, both disk and network I/O and stuff like that, when you only want agreement between two components that are in process,
right?
And living into different threads. And in order to solve that problem in a more neat way, in a much more performant way, we use something called software transactional memory that gives you transactional memory. It basically gives you what you have in Oracle. I mean, we begin, commit, roll back, but in memory instead. So it's extremely fast, and that solves a set of problems that you can't solve with actors. And on top of that, we have another couple of different abstractions over concurrency and over distributed computing that solves yet another set of problems. So Akka is more of a toolkit. It doesn't sort of dictate the rules. So you need to do it like this and that and so on. It more gives you a set of sort of orthogonal tools with that has high cohesion that you can use nice together and mix and match to solve your problem.
Right. So let's maybe look at these various tools, building blocks, components, modules, right? Let's start with actors. We did have an episode on Erlang a long time ago. So people might have heard about actors, and there are obviously also other languages and frameworks that allow actor-based programming models. But I think it's still useful to give a quick recap of what actors are, and then we can discuss what they are or how they are specifically implemented in Akka.
Yeah, sure. Yeah, actors are. You can think about actors very much as objects. They encapsulate state and behavior. They are, however, more encapsulated than what you have in standard classes in many OO languages and instances in many OO languages. In a way, they are more object oriented than what anything you can find in Java, C++, and so on. They implement what is called share nothing share nothing sort of encapsulation of state. That means that the state inside an actor cannot be viewed by any other actor. It can't be accessed in any way. So there's no way another actor can influence the sort of the state of another actor without sort of sending in a message and telling that actor to update his state internally. So it's a completely, the other end of what we are used to in Java, where we have what is called shared state concurrency, where everything, even though you might encapsulate your objects nicely into classes and use private variables and stuff. In the concurrency environment, you haven't encapsulated anything, because threads, they don't obey these rules. They run into, just straight across your classes and your instances, I would rather say, not sort of playing again with any of the encapsulation rules that you set up in your type system, and that means that you need to do a lot of plumbing in order to introduce sort of safety and determinism into your code by adding locks. However, the actor model is sort of raises the abstraction level in a way that it solves that problem for you. Actors are by themselves, the nature of actors are that they are thread safe, and there's no way you can get stale data, race conditions, and so on within the actor itself, and so all the plumbing is sort of taken care of for you by the runtime, and you as a developer can instead focus on writing the business logic, and the concurrency is actually lifted from plumbing to workflow. So with actors, you think in workflow, how messages flow in the system,
right?
Instead of how you should protect yourself from others by introducing locks.
So I guess that's maybe the core thing, right? So that actors only communicate via message passing. That's the only way they can talk to the outside or specifically to other actors.
Exactly. So the way that actors are different from objects is also that each actor has a mailbox. That is sort of a message queue. And if I want to communicate with an actor, I need to send it a message, and that message will end up in his mailbox. And it doesn't mean that if I send a message to an actor that I will sit and wait until that message has been processed.
Right.
But if you're used to programming with JMS or MQ series and so on, the model is very similar to that, in that messages are sent in an asynchronous fashion. Some people call it programming without a call stack. So it doesn't. The only thing it does, it puts the message onto the receiver's mailbox and it returns.
Right.
And then it's up to the scheduler to dispatch that message onto that actor. Whenever it's that actor's turn to get the time slice for processing on a thread.
And so from an actor's implementation, or from the perspective of somebody who writes an actor, you basically put in a repeat forever loop that looks into the mailbox and sees if there is something and maybe blocks if there is nothing, and then unblocks if there is something again, right?
Yeah. Kind of, yes, but the important difference is that actors never block.
Right.
They only block conceptually.
Of course.
So actors are completely, they are sort of lazy. They are reactive in a way that an actor doesn't do anything unless it's being told. And when an actor is sort of blocking conceptually, if she's blocking in quotes, it is suspended. So it doesn't consume any resources while being blocked.
What I meant by that, it's not an active while loop that really drives around forever. If there is nothing in the mailbox, the thread that owns the actor or the other way around is kind of suspended, and it's reawakened if there is another mail in the mailbox, message in the mailbox.
Exactly.
Right.
And what this allows you is to write systems where you have where you have not only thousands of actors as you can have with threads, but you can have tenth of thousands, hundreds of thousands, easily millions of actors, because actors are only constrained by memory. That's the only resource that they consume.
Well, but you still have to have a kind of thread pool that you allocate dynamically to an actor, and in some sense, this size of this thread pool maybe limits the number of concurrently active actors, right?
Yeah, absolutely. Sure.
Okay. So more cores give you more performance because more actors can actually run in parallel.
Yeah, that's, of course, that is very, very important. Yeah.
Right. So you said that there is absolutely no way actors can communicate with the outside world, and they have no shared state with anybody except through messages. So that basically means that those messages have to have value semantics, in the sense that the data that's passed from one actor to another one is kind of passed by value, not by reference, right?
Yeah, that's right.
Okay.
That's very important. And in Erlang, it is easier, because in Erlang each actor has his own heap. You can say that is completely isolated from another actor's heap. But Akka is implemented in Scala that runs on the JVM, and then on the JVM we just have one single massive shared heap.
Yep.
So this actually puts a little bit of a burden onto the developer, that the developer needs to make sure that all messages are immutable.
Okay.
That is exactly what you said. I just wanted to stress that is a limitation that is hard to avoid living on the JVM.
Yeah. So, but I mean, if you have actually distributed actors on different VMs or different machines, then you obviously have copy semantics or value semantics. You can't even avoid that. But if you're local, then that is actually kind of an overhead. So is there some kind of clever optimization that really uses, pass by reference, but it kind of really, I just got it. Because it's immutable, you actually do pass the reference, but nobody can change it. So it's,
We do. Actually, we don't do anything. The JVM makes sure that it optimizes that for us, right? So and in a way, that is one of the reasons why actors implementations in general on the JVM, if they are well written, can easily outperform actors on Erlang. But that is I will probably get flamed for saying that because it's always, in micro benchmarks you can prove anything you want, but that is an advantage, I would rather say, that we have.
Right.
It's more a burden for a developer, but on the other hand, you can get way better throughput by avoiding a lot of copying. So.
Yeah. So I learned that one difference between Erlang and Scala actors, or I should say Akka actors, because Scala has its own actors as well, is that there is actually pass by reference, and you use value objects to make sure that you don't actually kind of share mutable state. Are there other significant differences between Erlang and Scala? I should say Akka.
Sure. there are syntactic differences.
You're right. Sure, of course.
But I would say, there are a lot of people coming over from Erlang to using Akka actors, and they usually feel pretty much at home, because we have tried to maintain a lot of the same semantics. So there should be very few surprises coming from Erlang. Erlang has been using actors since early 80s, right? Yep. So and it's the de facto sort of standard for how to implement actor-based concurrency, you can say. Yep. So we felt that we didn't want to take a step away from that more than necessary. And there are areas where we have perhaps taken a different route, but in most cases we have not.
Okay.
So the main difference is in the runtime, I would say. How the JVM behaves compared to the Erlang VM.
Okay. It's interesting to see, because I always thought that one of the reasons why Erlang is as great and scalable and cool as it is because of its runtime. I always said kind of Erlang is more like an application server or framework than a programming language. So
it is. Erlang is amazing, right? but I would have to say it's very much depending on your use case.
Yeah.
I mean, Erlang is a dynamically typed language, and sure you have high performance Erlang, the hype optimizer. But on the other hand, my experience using both, and although I've lived most of my life on the JVM, is that I mean, for writing really high throughput, low latency applications, almost nothing beats the JVM. If you're using the JVM the right way and not complicating things.
Right.
It's so extremely good at optimizing things. So I wouldn't want to use anything else. But,
okay. So there are, I mean, I said that a couple of times, unfortunately. So there are also actors directly in Scala. They're actually a part of the Scala runtime or standard library. Why not use those? How are your actors different than those in Scala, standard Scala?
Yeah, the first iteration of Akka I was using Scala's library actors, so to speak. But I moved away from them and swapped them for my own after having some problems with them. We had performance and throughput issues, and then we also had some memory leaks and so on. And so that was sort of forced into creating my own actors. Also, I wanted to have a much more sort of open implementation in terms of how you can configure things.
Right.
We have tried to make it almost every little knob open, so you can tweak and tune, and we have different schedulers that you can swap, and and they can make a huge difference in different kind of use cases, yeah. So I think we've sort of taken the Scala actors and pushed the limits even further, and now we're working on replacing the Scala library actors with Akka actors, but not leaving all the Scala actor developers out in the cold, because we're going to re-implement some of the features that the Scala actors have that Akka doesn't. So we sort of going to try to make the best of both worlds. Okay. But that is not something that's going to come in Scala 2.10 probably in about a year or 9 months or so.
So one thing I never really understood is the following. So there are kind of two, in concurrent programming, there are maybe three kind of hypes or hot topics. One is actors. The other one is STMs. We'll talk about that in a minute. And the third one is functional programming. I understand why functional programming is useful. You know, you don't have any side effects, blah, 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 value semantics, blah, 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 all great. How do functions and actors fit together, or don't they fit together? And it's kind of an accident that Scala as a functional or object-oriented functional language has actors. So is there any benefit of having functional abstractions with actors together?
I would say, I mean, that's a very good, intelligent question. It is the short answer is that there's not much in common.
Right.
But a little bit longer answer is that I normally use them both together, because I use actors a little bit more coarse-grained to implement more components and services, and inside the actors I use functional programming.
But so I understand, for example, that the way the Akka actors are written, a kind of, if you will, a kind of internal Scala DSL uses functional things and, you know, closures and stuff, I think. But what you just said is basically if you use functional programming within actors, then this functional program or these functional programs are not concurrent anymore, because your unit of concurrency is the actor. So you use functional programming just because it's more concise and nicer and higher order functions, blah, 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 but not for any concurrency reason.
Yeah, exactly.
Okay.
But I mean, the main, we do have something called agents that takes the functional angle, the functional perspective on actors, you can say. And I'm just going to explain them in a second. Now, first, I just want to explain the reasoning why we wanted to add them, and that is that actors are a little bit hard to compose, because they are objects, right? And they are object oriented in the normal way you do like abstractions and reuse in OO is through class inheritance, and that is normally the way you compose and you extend and reuse actors. However, in the functional world, you don't want that. You want function composition, right?
Yep.
And that's why we added agents. Agents is something that we haven't invented ourselves. It's something that comes from the language closure,
right?
And it's a very neat way of using the actor style, but from a functional perspective. And what agents does, we talked about actors having encapsulating state and behavior, and you're sending immutable messages to an actor. So basically, you're sending stupid state asynchronously to the behavior, because the behavior is inside the actor.
It's basically like components. You have a procedural interface in some sense. Okay, it's asynchronous, but the behavior is all in the components, aka actors, and then you send around pure data.
Exactly.
Like back in the day.
Agents, however, they invert that. An agent is basically a memory slot that you can put something in. A bucket. You can put a map in there, or a vector, or just an integer or something. Mm-hmm. And an agent allows you to send asynchronously. Instead of sending a stupid data holder or an immutable message, you can send a function to the agent asynchronously and have that being applied in an atomic fashion to that bucket.
Right, but that works only in process, right?
Pardon me?
This works only in process, or is this also possible to do remote?
Akka's actors currently are only in process, but nothing would prevent us from doing them remote, because they are internally written using actors, and we have remote actors. So but it's not been something that people have asked for so much. Mm-hmm. But nothing would prevent that. But the whole idea is that instead of sending state to the behavior, you're sending behavior to the state. And now, since you are sending a function, you can compose that function in any way you want before you send it. Mm-hmm. And that means that you can use this agent differently, even with different implementations, depending on context, from where it's being used and how it's being used. And so this is the way you can approach sort of the asynchronous actor message passing style model through a functional lens.
Okay. Am I kind of wrong, or does this already kind of lead into the STM story? Because I think the way software transactional memory is implemented in Clojure is, at least one of the mechanisms is also these agents, that you have something where the access to shared state is kind of controlled and guarded, and what you do is you send functions and they are kind of coordinated through a kind of mailbox, right?
Yeah.
So is it a good time to talk about?
One thing leads into another, you can say, because what these agents are, they are transaction aware in Akka, and they're also in Clojure.
Right.
So what they are is that what they do is if they are being applied, if the function is being applied to an agent, then it will look out in the context and see, is there a transaction running? If there is a transaction running, then it will join that transaction. And what this means is that the function will not be applied to the agent unless the transaction commits. So it will hold off until there is a successful commit of the transaction, and then it will flush this buffer of functions. And that means that you can compose them. So you can have many agents joining the same transaction, and you know that either all are applied successfully or none are. And also, agents are similar to how STM is used in Akka, because STM in Akka is used using what is called managed references. And those also happen to be memory slots.
Right.
But the difference between these managed references and agents that are used in a transactional fashion is that agents are asynchronous, why the managed references are not.
Okay. I see. So I mean, we don't want to do audio programming here by having you read source code, but can you give us a little bit of a flavor how the API for actors and for this agent stuff kind of looks syntactically? I mean, just a little bit of an idea.
Sure. Starting with actors, if we're looking at first, I want to say the Scala has a Java and a Scala. No, Akka has a Scala and a Java API.
Oh, okay.
So you can use everything we said, SDM agents and actors from Java as well.
Just requires 10 times the amount of code, I guess.
Yeah, sometimes. Not always though.
Okay.
We've tried to make it concise. But
okay.
but if we want to talk about the Scala API now, since we've covered we're sort of coming from a Scala angle already, is that if you want to implement an actor, we have something called we have a trait called actor, and a trait is just like a mix-in. It's an implementation like an interface with an implementation. So you can mix that into any kind of class. But basically you say whatever foo extends actor, and then you need to implement one thing, and that is the receive method. And the receive method implements the message handler for that actor. And in Scala, we're using pattern match to match on the message that comes in. Cool. So basically you have case message 1, case message 2, case message 3, and then it does matching on which message arrived in the mailbox and is being dispatched now, and then it runs the handler for that message. That's basically how it's what it looks like. Mm-hmm. And all code, all state that you have now inside the actor as member variables are completely thread safe. Like you need to have it as volatile or atomic references and stuff like that. Mm-hmm. Okay. An agent, however, is less code because it's just a memory slot. So if you want to write an agent, you only say agent and then parenthesis and then whatever value you want to put in there. You can put in a map, or you can put in something else. You can even say you don't want a value, you just want to type. You can then say agent square brackets int, for example. Mm-hmm. And then you have a message, a method called send, that you can send a function to that agent. So that's basically what it looks. The SDM is very similar. Then you just say ref, ref, and parenthesis, and then you wrap the value. And then that value is then managed by the SDM and fully transactional. Mm-hmm. And we also have transactional data structures that gives you a standard Scala map interface, but it's transactional under the hood. So then it removes almost all sort of visible traces of the plumbing, so to speak.
So when I came across transactional memory first time, I don't know when that was, I kind of always saw this keyword atomic, and then between the braces you would do stuff. And Clojure as well as Akka use a more explicit way of doing things by explicitly putting those memory contents that should be transactionalized into these references, and then you have to explicitly interact with the reference instead of with the data that the reference holds. Is that just syntactic sugar, or is there a difference that I don't seem to understand?
You're talking about why we are both Rich Hickey and Clojure and Akka is having a very explicit way of using SDM.
So it's not all of the memory is transactional, right? Only the things in the you explain.
Exactly, and the reason is basically because I've historically been a bit skeptic with SDM. The early SDMs they used a lot of magic, bytecode rewriting, basically allowing the user to mess around with his state in any kind of weird ways, and then the SDM would just come in and bless the whole thing, and it would just work correctly. Yeah. And I'm a non-believer in that, I would say. Okay. I think that it's being explicit, if it's not too much verbosity in the code, is a good thing, because you know when you sort of both pay the price of the performance hit, but also you know explicitly when sort of the STM is affecting your code, and you can be very, very, very fine grained in which state needs to be transactional and which state should not be transactional. And I sort of like being explicit. The actor model is a very explicit way of concurrency, and not trying to like lie or sort of pretend that we have shared memory, even though we don't.
I mean,
and the STM is sort of an extension of that. I want to have it explicit.
I think this is a general tendency, right? I mean, when you look back at the beginnings of OO, everything was an object, and everything tried to make it look like local object-oriented communication. Also, even if the objects were remote, like in Corba or Java RMI, and then you had these orthogonal persistence thingies, right, where you would automatically persist objects and so on and so on. But of course, the non-functional properties of remote or persistent data are completely different. And now I think there is a tendency to make these things explicit and not try to hide it. You can see that in ZOA or REST, and as you just say, also in your kind of STM implementation. I guess that's maybe a general tendency, right?
Yeah, I think it's a healthy tendency.
Yeah.
Some things should not be hidden. I think, and concurrency is one thing, and that is easier to hide. But the network is almost impossible to hide.
Yeah.
I mean, if you want to hide the network, you will always lie, regardless. I mean, sometimes you lie better and sometimes worse, but it will always be a lie. Like it's a very, very leaky abstraction that leaks way too much in most implementations I've seen that tries to hide this.
But actors are remotable in Akka, right? And there the syntax doesn't change. So in that sense, that's transparent.
Yeah. And that is that was sort of one of the key things that we wanted to achieve. That you write your actors as these living things, like these active components, and it shouldn't matter if they should be used in a single-threaded environment, in a multi-threaded environment, or in a multi-JVM environment. And what we do, instead of trying to raise abstraction so much so we hide that everything is local, we actually do the inverse. We say that everything is as it is distributed.
Yep.
So we use message passing, even though it's in process. We always use message passing, and that allows us to like stretch it out onto multiple JVMs or even data centers without sort of lying. That is shared memory. So actors really implement completely location transparent distributed computing. What you do is that when you create an actor, you don't get an instance or reference to that actor directly, but instead you get a reference to that actor indirectly. You get a pointer. In Erlang, you have something called PID, the process ID. Yep. In Akka, it's called actor ref. And it's the same idea. So this PID, or this actor ref in Akka, can be used in process and to talk to a local actor, but it could also used on one machine to talk to a remote actor. And the client doesn't need to know. He just sends messages.
And are these then kind of proxies with a strongly typed interface that only allows the messages that you kind of handle, or are actor interfaces generic in that sense that they accept any message and then they're kind of discarded if you don't know how to handle them?
Yeah, that's a very good question. That leads us into Akka's two different types of actors.
Okay.
We have the classic sort of style of actor is dynamically typed, you can say. Even though Scala is a statically typed language, the way we implement actors in the classic sense is making them sort of dynamically typed. What that means is that you can send any kind of message to an actor, and it does dispatching on what kind of type it is, basically. But it uses Scala pattern matching to be more intelligent than just instance of.
Yeah.
And that means that you can send messages to an actor that an actor cannot respond to.
Yep.
That is something that you need to deal with. But on the other hand, what you can do and what we do allow in Akka is to swap the actor implementation. So there might be different sort of stages in an actor's life cycle. You can see an actor as a state machine, and in a specific when you start up an actor, it might be able to respond to one or two or three types of messages, but then it can internally swap its implementation to be able to receive another type of messages. So it can change its API basically, and then messages it can respond to dynamically.
Of course, it doesn't change the API, right? It's not visible to the outside what the inside can handle now. So that I guess that's the thing, right?
That's the thing, yeah. And that's that was one of the things that I found very powerful in Erlang. Erlang being a dynamically typed language.
Yeah, it's natural there.
But we were able to encode that in Scala in a way that feels very natural. So you can, if from within an actor, you just say become, and then you pass in the new implementation. So then you can sort of say, I want to become something else. But you can also send an actor implementation from the outside by sending a hot swap message. That is less useful, I would say, because it's a little bit more dangerous. But it can be useful sometimes. But I tend to use this become. The actor can redefine itself very often, actually.
Mm-hmm. But that is basically the bridge pattern, right? You have different implementations for the same thing.
Yeah.
You also have typed actors, right? Do they have a strongly typed API then?
Yeah, it does. And that can be very useful sometimes. Basically, what we're doing then is allowing you to encode actors by using an interface with the standard methods, interface in Java or a trait in Scala, and then a regular POJO, regular standard Java object, Scala object as the implementation. And then we rewrite the internals of that sort of code. If you would just create it using new and then whatever class it is, then it will become a regular standard object. But if you instead create it through a factory that we have, then what we are returning is sort of something very similar to the active object pattern. That each time you sort of invoke a method on that interface, that method is turned, or that method invocation is turned into a message. We wrap all the arguments to the method into a message and put that asynchronously on a queue to be processed by the internal POJO.
But when it reaches the POJO, it's again kind of turned into a method call on the POJO.
Yeah.
Okay, so there's basically an indirection and a queue in between the actual kind of interface and the implementation.
Yes.
Okay. Mm-hmm.
And we rewrite void methods into fire forget, and we rewrite something methods that return something. We rewrite to methods to message send that returns something called a future.
Okay, cool. Mm-hmm. Nice.
So you can sort of use any kind of method dispatch, both sort of fire forget and also request reply.
What do you do with exceptions?
We make sure that we transfer them from the receiver's thread into the caller's thread and throw as expected.
So they're thrown on the proxy.
Yeah.
Asynchronously? No, can't be.
No, they are thrown whenever they happen in the sort of receiver's thread. We using the standard sort of message passing. So we pass a reply method back into the caller's thread, and there we throw an exception.
Okay. So how? But I don't get this. How does this work with the futures? Because I mean, futures are an object you get, and then you, as the client, you kind of ask the future for the actual value whenever you feel ready, and maybe the value is there, maybe it's not there. So it's kind of a poll mode. But then, if you use kind of how do you when and how do you throw the exception? I mean, the client might be off doing completely different things.
Yeah.
How does that work?
Good question. I wanted to write some code here if I could, but basically what we have three different ways of doing it. If you only return, for example, a string, if you have something that passes a method that takes a string and returns a string, we do not expose the future to the end user, but we inside the implementation we get the future, and then we do an await without returning the value until we get either the timeout, we get an exception, or we get the return value.
So from the client's perspective, it's like a blocking call.
Yeah, exactly.
Okay. Mm-hmm. Then I understand where the exception is thrown, right? That makes sense.
Yeah. But we also allow you to actually in the interface create a method that returns an Akka future, and in that sense you are in control. That method call will return immediately, and you can decide to do the blocking await, or you can register an on-complete callback to let them know, or you can check did it complete with an exception, did it complete with the value. And so on.
Okay. So, but if you do a proxy with a blocking call on the client side, then the whole benefit of the actor model and the asynchrony only shows up on the server, which becomes more scalable. The client kind of will have only a limited number of kind of threads, and if they're all blocked, then the client is out of luck.
Yeah.
Okay.
Yeah. We do have the same request reply kind of style of development for this untyped, for these dynamically typed actors as well.
Yeah.
That allows you to send a message and then just say reply, and it will reply with the future. But we are trying to tell people to avoid using blocking future calls as much as possible. We have shown in benchmark that it can limit your throughput by to 1/3 of what you could get if you're using unblocking calls.
Yeah, because you're introducing some kind of synchronized blocking thingy again, which is the problem, right?
You're sitting on the thread,
yeah.
and you're consuming resources, and if you do that for like X thousand simultaneous calls, we can run out of threads.
Right.
But what we have added now in Akka 1.1 that just came out a couple of weeks ago is a completely non-blocking API to futures. So it allows you to get a number of futures and work with them, composing them even without blocking, and then so you can actually do operations and calculations based on not yet completed values, and you can choose to block on the final computation. And delay it as long as possible. And it also, we even added something called the on-complete callback, so that allows you to register a function to being told when the value arrives. And if you use that, there is no blocking at all.
Right. So, but that requires some Scala magic, right? You can't do that easily in Java, at least not with an acceptable syntax.
No, you need to have this ugly interface sort of style of functions, right? So you new function and then implement the run method and stuff like protocols, stuff like that. So it's a little bit more code.
So I was going to ask you why you selected Scala. I mean, is it just because it was the language of the day, or were you just interested, or does Scala have any specific properties that makes Akka? Well, I mean, of course, you can implement everything with ugly syntax like in Java, but how important is Scala for making work what Akka does?
Yeah, I think what it mainly enabled me was, and now us, is to deliver the Akka platform at runtime so much faster. I think it is using immutability at the core, using all the excellent data structures inside Scala, and so on has. I mean, I've been writing similar systems myself. I mean, being part of Terracotta, writing scalable middleware and BA, WebLogic and stuff. And I feel that I'm much more confident in the code that I write in Scala. It's less bugs, it's less code to both write and to maintain and to understand. It lifts the abstraction level, so you can more reason about the actual implementation value rather than a lot of plumbing, I think. Right. And it also fits very nice with Scala, our whole approach of immutability and embracing concurrency. And I also think that I could have, of course, I mean, in due time, written the same thing with the same performance in Java. But the amazing thing is that Scala can actually gives you the same performance and the actually almost identical bytecode as you get with Java. And there aren't really any languages out there that runs on the JVM that can give you that. Most other languages are dynamically typed, and they are out of the question. So Scala can really take. I mean, they can really, at least for what I'm writing. I mean, there are many people using it for web applications and writing stuff that aren't performance critical. But I could never use it to write middleware. But I can use Scala to write middleware in the same. We can really take Java's place there, and I think that's pretty amazing.
Mm. So let's talk a bit about fault tolerance. You already mentioned that you use Erlang's "Let It Crash" style, which basically means that one actor monitors another one, and if the other one dies because it crashes, then this, it's kind of a new one is started. Is that kind of a correct summary?
Yeah.
So
that sounds very well.
Why
we use it?
Yeah.
Basically, because that allows us to write system that can heal themselves. You can declaratively configure the way the system should respond to failure. Instead of in standard classic Java style error handling, you literally first you have what your sort of critical state. The real core business state you usually have littered throughout the whole application. Secondly, you normally program extremely defensively by using try catches everywhere. You're paranoid, you're trying to prevent error from happening. But if you write systems like this in high performance and especially distributed computing, you know that failure is imminent, right? There's nothing that you cannot prevent. It will happen regardless if you want it or not. And instead of trying to code it defensively, this way of writing fault-tolerant code embraces failure and sees it as a natural state in the application lifecycle. It is as natural to crash as it is to boot up and to start and to dispatch messages successfully. And this gives you a way of thinking about the problem. Basically, that first it gives you a granularity of programming, the failure management that sort of can help you to have the system repair itself.
It's kind of like a global exception handler, right? If something goes wrong, restart it, please.
Yeah, I mean it doesn't perhaps fit all problems, but I've used it in a whole wide range of different problems at clients and with a lot of success. And basically, I mean, the whole idea is that you should sort of reset your components into stable state and continue.
Right.
And the way you normally organize your programs like this is to write them like an onion. So you have your innermost critical state inside innermost inside the onion, and then you have layers of defense, you can say. So you have first line of defense, the second line of defense, the third line of defense, and the request coming in from a user usually hits your outermost line of defense, and then it usually takes a lot from for the error to propagate all the way up into the innermost critical precious core of your system. Mm-hmm. The way I normally write my application is that if I'm holding on to some critical state that is important to me and I'm supposed to do something, then I never do it myself. I always create an actor and delegate to him to do that for me. If he dies, that's fine because I'm still okay.
Right.
And so by having this level of indirection, I can protect myself in a very nice way. And this whole thing becomes completely declarative. So you declaratively define the rules for how this should set up, and the system take care of it by itself.
But I guess setting up those rules then and the relationships between the actors and who checks who and who restarts who, can be non-trivial, right? I mean, getting something wrong there, that means everything is screwed. How do you test this? How do you get confident in that?
Yeah. that is something that we're working hard on in the Akka team right now to create good tools for testing. I think the problem is wider than just testing the components for failure. It is that also that you normally tend to run all of these components in different threads, and so it becomes a problem of testing things concurrently very, very easily. We try to help with that by, for example, providing a dispatcher that basically forces you to dispatch everything in one single thread. So you get sequential, serialized so communication, and that makes it much easier to test. And we also have other tools in the Akka test kit module that allows you to sort of test this concurrent world in a more deterministic fashion.
Okay.
Basically, but it is a challenge, definitely. But I think it's no less challenge than testing in Java style applications,
sure.
with try catches,
sure,
everywhere. I think it sort of lifts the problem a little bit to another level, not simplifying it, but you need to approach it a little bit differently.
The good thing is, I guess, you have a clearly defined set of, let's say, boundaries or interfaces, which are the actors, and therefore putting in some kind of tracing functionality that gives you a time diagram or, some printout or whatever that shows the timing of the different interactions is easier to do than kind of if you did that on any level within the implementation code.
Yeah.
So.
Yeah, definitely. And another thing that is also worth adding when we talk about this is that if you want to write a concurrent application in Java, you normally use, for example, an executor service and a thread pool, and you dispatch callables to do jobs.
Yep.
If these die, even though you have a try catch or whatever, and try to repair it. If the thread blows up, the only thing you will see is a stack trace all the way up to your Java executor service, normally, because exceptions do not jump between threads, right? There's no way another thread can be notified that my buddy thread died here.
Yeah.
But using this sort of linking and supervision, that is also called, allows you to monitor other concurrent components and get notifications across threads, which is a very non-trivial problem in writing concurrent code.
Right.
So I just personally love that. I mean, it's a lot of problems to go through to fix that if you write standard Java multi-threaded applications.
So I guess we kind of covered the core of Akka, right? The most important things we covered, I would think.
Yeah, I think so. I think the essence. That is the three sort of cornerstones are the concurrency, scalability, and fault tolerance. So I think that should be the essence of Akka, at least. Yeah. Then we have a whole bunch of other modules for interacting with the rest of the world. You can say, like for other services and other modules and other stuff.
I think you should give us a brief overview, at least, of this stuff. I mean, for example, I wonder what the Spring integration is all about, and AQMP or OSGI, REST. I mean, just give us a little bit of an overview so we know how to connect it to our existing world.
Yeah, sure. As you said, we have a Spring module, and for that we're integrating the Akka's typed actors into Spring. Since Akka's typed actors are essentially Spring beans, you have an implementation with an interface. It's very natural. We have a Spring sort of DSL, you can say, a custom namespace in the application context.xml that allows you to wire up, even supervise the hierarchies, and creating remote typed actors, so all within Spring, so to speak. And it uses you can use your standard Spring dependency injection to inject stuff into your actors and stuff like that. So that's pretty neat. We have similar for Google Juice as well. If you're introducing Google Juice, that also using the typed actors to sort of slide into the Juice world nicely. Yeah. Then we also have you also mentioned briefly AMQP. We have an AMQP module that sort of abstracts AMQP as actors in a way.
So what is just to be sure people know what is AMQP?
It stands for Advanced Message Queue Protocol. It is a standard a bunch of investment banks led by J.P. Morgan created because they felt they were in the hands of the big message queue member brokers, MQ series and TIB, and they didn't want to pay license fees any longer, so they created their own specification.
Okay.
And that's a specification that's taken off. And it was initially a brilliant specification, and the latest revisions have received a lot of criticism because it's been complicated. But I still think it's a pretty slick specification.
How does this integrate or play together with the Java? What is it called? Java Message Queue, Java Messaging Interface, JMI, right?
Yeah. I'm not really familiar with exactly how it relates. Something
in common.
Yeah, but most the JMS brokers now are starting to implement AMQP protocol.
Okay, I meant JMS.
You meant JMS.
Yeah. I forgot the actual abbreviation, so of course.
Yeah, I was thinking I was too sleepy now to understand what you were talking about. No. JMS. Yeah. So yeah, we're starting to see some consensus.
So you would use JMS as the underlying communication transport technology that transport messages between actors.
Yeah, I think the other way around actually, because AMQP is a network standard. It's a binary protocol. So it is a protocol on the network layer.
Yeah. Okay. But
and you probably you could use the JMS API, but the communication is all in underlying AMQP.
So, but if we forget JMS for a second, just talking to AMQP means that your actors are still the same, but you plug them in so they receive messages through AMQP.
Right.
Okay.
Exactly. The protocol for communication is now AMQP instead of Akka's standard TCP-based protocol.
Okay, basically. Get it. Yeah. OSGI, is there a story?
Yeah, we had an attempt to make everything in Akka OSGI enabled, all the modules, but there was too much pain in that, so we had to revert that. But currently the Akka core, the Akka actor.jar, in which you have all the actors and that stuff is OSGI enabled now. So if you only use that, then you can use OSGI. But apart from that, I have to let my users down, unfortunately.
I guess Heiko will solve that problem at some point.
Yeah. He was the guy trying to solve it, but he backed out.
Yeah. Okay.
Another module that I just wanted to make sure that we cover is the Akka Camel module.
What's Camel?
The module for Apache Camel.
What is Camel?
Pardon me?
What is Camel?
Camel is a framework to implement enterprise integration patterns.
Ah.
It is basically DSL, domain specific language for wiring endpoints together.
Mm-hmm. Cool.
So you might have stuff flowing in from JMS. You want to pipe them through using some sort of routing and perhaps replicating something to AMQP. You want to shovel something down into MySQL database at the same time that you want to shovel it into some other thing for auditing. Mm-hmm. And you can basically connect all these endpoints together in intelligent fashion and have some plumbing done in between. And Akka abstracts that. So you basically, if you look at it from the code perspective, the only thing you do is that you take a regular actor and say with consumer, and then you define one single field with a string defining the protocol. So if it should, for example, if you define it as HTTP, for example, so if you say create a consumer, say HTTP, mm-hmm. and then you start that actor. That means that if a user, for example, comes in and browses to that HTTP URL and posts something, it will end up as a message inside my actor, and I can act upon that. And then I can just say reply to post something back to the browser. And the nice thing is that if I want to change the endpoint, I only need to change one single line of code. For example, from HTTP:// to, for example, JMS.
Yeah.
Then it becomes an actor that receives JMS messages, consumes JMS messages. If I change it to AMQP protocol, it consumes AMQP messages. Mm-hmm. And you have the same thing for producer. So everything is actors. It looks exactly like actors. You send and receive messages, but they end up and flow through these all endpoints. And it's a very slick way of having Akka interact with the outside world.
Mm-hmm. Cool. Is there also a REST story? I guess everything today has to have some REST story.
Yeah, Akka has an HTTP module that has a sort of an implementation that was initially called Mist. I don't know if we want to rename it. But that gives you asynchronous.
You know what Mist means in German, right?
Yeah, no, okay, I've been told. So that's one of the reasons why we're thinking about renaming it. Yeah. That I was also told by some Finnish developers that Akka apparently means something not that good in Finnish either. But it's hard to find names in all languages.
Right.
Yeah, so this Mist layer gives you asynchronous HTTP, and it uses first it used Jetty continuations, but now it's using the Server 3.0 spec to be able to resume and suspend and resume the HTTP connection, and in an actorish way. But basically you get messages with the put, get, post, all this stuff sent to your to your actors in a slick way. It's a very low level API. But there are other guys that have built pretty interesting stuff on top of it. There, for example, one framework called Spray that have built a sort of Ruby Sinatra style DSL on top of this Akka Mist low level layer.
What is it called? Spray?
It's called Spray, yeah.
Like
SPRAY.
That's
spray.
Funny.
Yeah, as in hairspray.
That's funny. We just talked at a conference about creating another DSL for graphical DSLs called Spray. I guess.
Okay.
Okay.
You should Google it.
Yep.
Yeah.
I guess so. Okay, so
and we have some other modules as well. I mean, one worth mentioning is the FSM module for Finnish state machines. Actors are often state machines, so that's why it can be worth looking into that.
Right. Okay. So let's kind of wrap up by kind of zooming out again and talking about how and where Akka is used. So how does it scale, and how do you know?
Yeah, that's a very good question. We have of course not tested it up to the number of nodes that we would like to, because it's a cost issue. But so the biggest installation that clients have tested it in is 274 cores. Mm-hmm. Yeah, so that was a pretty big installation, and they were very pleased with that, and it passed with flying colors. I can't mention the source for it, but it's a pretty big installation, and so apparently it seems to do its job well, and sometimes to my surprise that it seems to work as intended. So I'm not always, of course, but then we need to go in and fix things. But it's been out long enough now, and it's been used in production in some cases for more than two years. Mm-hmm. So we've been sort of reaping the benefits of it being a public open source project for so long. I mean, people have contributed ideas, patches, bug reports, and so on for long, and due to that, I think it's in very good shape. Mm.
So, are there any citable uses from known companies that use the stuff? So, as a way of kind of dropping names.
Some. There's no need to think through, so I don't mention anyone.
That's always the problem.
But some of them are it's companies like Swedish Television are using it.
Mm-hmm.
CSCC in Netherlands is a very large installation using it. What else?
And they use it mostly as a backend for web applications. Is that fair to say, or enterprise applications?
It's actually being used in quite different areas. I would just say it's always. I wish I could just name all of the companies we're working together with and what they're using it for. But I can't. But in short, I just want to say that most usage is actually out of the finance industry. Mm-hmm. So it's not e-commerce. It's usually trading applications, right. A lot of transactions per section, high throughput, low latency. It's also been used in betting gaming for very similar use cases. You have huge number of transactions per second flying in. MMO games as well as standard, I would say, but a more classic like betting, casino style, and also like sports betting style companies. It's also used in simulation and for like sort of massive data set crunching that they have in doing simulation technologies and also some e-commerce, of course, but it's not the biggest sort of segment, I would say.
Okay.
But we have a lot of social media and so on as well.
I remember that Twitter uses Scala. So do they use Akka as well?
I don't think they are using Akka actually. Still, okay. They've been writing a whole bunch of homegrown solutions, but they are very heavily dependent on Scala. Mm-hmm. They are the same thing with Foursquare and some of these other hip community sites. Bank Simple, by the way, are using Akka. One of the hot upcoming.
Right. So is there a story between Akka and Lyft?
I know that people are using them together,
but there's no specific like integration.
There's no real story. No. Okay. We don't integrate with any sort of web frameworks directly more than others have written adapters. So there's there has been some work done with Lyft and also with Play. There's an Akka Play module, for example, and also it also integrates with many of the Scala, the minor Scala web frameworks. But we try to, at least so far, like stay away from locking into a specific web framework. Yeah. We just try to make it easy to use with any kind of web framework.
Okay. So we were planning to record this episode last week, but I didn't have time. And originally we were planning to do it 2 weeks ago, and you didn't have time because, as I noticed afterwards, something big was happening. It's called TypeSafe. Do you want to talk a bit about it?
Yeah, sure. I'm really excited about TypeSafe. It's basically in my company, Scalable Solutions, that initially was a consultancy company under which I developed Akka, and then later became a product company around Akka with Victor and Victor Klang and some other guys. We were 5. Joined forces together with Martin Wodersky's company called Scala Solutions, then to build a stack on Scala. Scala as the foundation, and then a full-blown stack with middleware and tools, and also integration with various web frameworks and so on. So we joined forces. We founded the company back in January, but then we launched it about 2 weeks ago together with this offering, the TypeSafe stack that we have subscription support for. And so on. It's all still open source. We're planning on having some product suite, commercial products later on, but so far everything is just open source. It's a highly tested sort of package of Scala, Akka, and also later SBT, Simple Build Tool, and some tooling, IDE tooling, and so on.
You seem to have hired quite a number of people from the Scala world. I hear that Heiko is also going to be part of that group.
Yeah, Heiko starts June 1st.
Right.
So that should be tomorrow.
Yeah.
I'm very excited about it. We had some great developers from the Akka team and from the Scala solution, from Martin's team. But apart from that, we also have been able to hire some great minds. For example, the multiverse STM guy that Akka relies on the multiverse STM. Peter Ventier, he's part of TypeSafe now. We hired Mark Hara, who is the guy behind SBT, the Simple Build tool.
Cool.
And Paul Phillips is one of the co-founders. He's like the second guy in the Scala compiler after Martin.
Okay. Wow.
So there's a lot of great minds.
I hear you've also hired people from the Scala Eclipse IDE, so we can hope.
Yes, we're working very hard on that in the company now.
Yeah.
To try to make it, not only usable, but bring it up to eventually to the level of Java. That is the whole idea.
That'll be the time when I switch.
A lot of people say that, so that's why it's so important.
Yeah, if you have a strongly typed language with all the potential for this great IDE support, and then you don't have a good IDE, it kind of spoils the.
Yeah, I know. I mean, personally, I'm still hacking in a text editor, right? I'm used, and I'm so used to that. I've been living in Emacs and then in TextMate and so on for so many years now. So I don't even think about it. But I know it is one of our big challenges.
Right.
But I think we are about to solve it. The latest Eclipse plugin is very, very good, and now we have a dedicated team only making it better every release. So in 6 months, I think it will be very, very good.
Cool. So is there something we forgot to talk about? Anything else you want to say before we shut this down?
I don't know. Not more than I think it's exciting times for Scala, and I really encourage people to try it out and eventually, if they might have scalability problems, I think they should look into Akka. But there's also a whole bunch of other nice frameworks and tools out there in the Scala community. It's a fantastic community with lots of great developers and producing a lot of great stuff. So it's definitely worth checking out.
Yeah, if
you Java, you can still use Akka. It has a nice Java API, so that shouldn't prevent you from trying it out.
Scala, I think, is closest to becoming the next big language, I think, after Java. I'm not sure there will be a language that will have the same, general adoption as Java has or had. But Scala is clearly on track, I think. So it's very exciting, as you say.
Yeah, I also don't believe in another next big language, NBL, that people talk about.
Yeah.
I think we have it's so easy to create languages nowadays. Right. The barrier since we have the JVM is so low now, and people have gotten used to use many different languages, right? People are not that afraid jumping between. So I think we're stepping into the polyglot world more and more.
It's funny, just to kind of as a final comment, it's funny how although we get more and more languages, many of them have the core have similar features, right? It's basically functional, object-oriented, a bunch of meta programming, and then depending on whether you're dynamic or static, you have two different options, kind of. But there's a lot of common stuff between all these languages. Yeah, it is. I mean, it is converging, and a lot of the ideas are almost all ideas are old. Yes.
They all come from Lisp. And other languages are 40 years old or 20 years old. So we're starting to. I mean, we're almost made a full circle now. Just like what comes out this time is better than that was 40 years ago.
Absolutely. Okay, then thank you very much for being on the show. I enjoyed it very much. I really like these language middleware framework discussions, and I hope you liked it as well.
Yeah, thanks a lot. I was honored to be part of it. Thanks a lot for letting me be on the show.
Absolutely. You'll be able to read what the listeners think. I think they'll like it.
Yeah, cool. Thank you.
Thank you. Bye.
Bye-bye.
Thanks for listening to Software Engineering Radio. SE Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons, or by talking about us on Twitter and Facebook. You can also support us by joining the team and shouldering some of the work. To contact the team, please send email to team@se-radio.net, or if your feedback is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under a Creative Commons 2.5 license. Please see the website for details.